Hello everyone, my name is Elizabeth Ephraim and I am a data scientist and business analyst intern at the Sparks Foundation. I attempted task one of the GRIP November 2022 internship program. And task one was or is prediction using supervised machine learning. I attempted this task using linear regression because we usually use linear regression when predicting something continuous, for example, house prices, or in this case, student scores. We have two variables, the independent variable, which is number of hours studied, and the dependent variable, which is student scores. So the next step is to import all the necessary libraries as you've seen here, and then also bring in your data into Jupyter Lab. I'm using Jupyter Lab. So after I did all of that, importing pandas, SPD, importing NumPy, Seaborn, Matplotlib, and the rest of them, and then bringing in the data using this code. So student underscore data is my variable here. And afterwards, we can see that we have 25 rows and 2 columns. And yeah, 25 rows and 2 columns. So a great starting point for our analysis is a scatter plot. So this will tell us, or rather this will help us see, sorry, there was a typo here. So this will help us see if there's any relationship between the data in the first place. So plotting my scatter plot, X is for hours, Y is for scores. So the title is hours versus percentage, and we can see clearly just by looking at it. The longer the hours, the higher the score. We can see from our scatter plot. So from the above graph, it's easy to see that there's a positive linear regression relationship between the number of hours used for study and the student scores. So next, let us classify the data into inputs and outputs, or rather features and labels. So there's a quick explanation here. Features represent the different columns in a data set. Labels are also called targets. It gives a supervisory signal to the data. So what I mean here is if you have 20 columns, one of those columns will be your target column. Your target column gives supervisory signal to the data, like it kind of tells the data what to expect. Target is always only one column. Or sometimes you might have 2 or more columns that seem like the target. It will be left for you to decide which of the columns will be your target. So in this data, the scores column is our label or target, while the hours column is our features represented as X. So moving on now to classifying the data, X is equal to student underscore data dot ilog. And Y is equal to student underscore data dot ilog and dot reshape, because we need to reshape our data to -1 and 1. So moving on now to splitting the data set into train and test data sets. And usually we run this code when we're trying to train and test our data from sklearn.model underscore selection, import train test splits, and all of that. So just a little explanation, or rather a quick explanation. Our data set has 25 XY pairs. I mean, we already saw that above. So we've specified the argument test size to 5. This means we're going to test 5 out of 20 of those data, and then the rest of the 20 will be used for will be used for training. The data set is divided into training sets with 20, just like I said, observations, and a test set with 5 observations. The random state hyperparameter in the train test split function controls the shuffling process. So anyone wondering why we have a random state equals 0, here is why. Above, it's been set to 0 to control the shuffling process. By default, the random state hyperparameter is set to none. Usually when you do that, when you set it to none, it leaves the shuffling process out of control, and we definitely don't want that. So when it's on random state 0, like I mentioned, we get the same train and test sets across different executions. Moving on now, training the data set. Let's view the shape of the data. Okay, so we can see, just like I mentioned, 20 for training and 5 for testing. Fitting the model. Fitting the model means determining the best intercept and slope values of the regression line. And so we use this code from sklearn. We import linear regression. Linear regression, this is the variable I use, linreg equals to linear regression dot fit x train, y train. Linear regression intercepts gave us 2.0 and the rest of the figures. And then when we tested for the linear regression coefficient, we had 9.9, and the linear regression score is 0.95, and the rest of the figures. So one thing to note is the higher the linear regression value, the better the fit. Next, we move to plotting the regression line. Plotting for the test data. So again, I'm using a scatter plot, and we can clearly see that it's a great fit. The regression line is a great fit. And next is testing our data. We test our data using ours to predict the scores. So print x underscore test, y underscore prediction equals to linear regression dot predict x underscore test. And this was the result that we got. So let us predict the score if a student studies 9.25 hours per day. And then or rather, I did that by typing in this code, print predicted score, linear regression, predict, np.array, 9.25 reshape using these figures, -1 and 1. So the result was, if the student studies for 9.25 hours per day, the predicted score will be 93.69. The predicted score will be 93.69173249. So move on to evaluating the model, right? We have to evaluate the model to be sure. So, I did this using the mean absolute error. We'll evaluate the model using the mean absolute error. So just a quick explanation. The mean absolute error is a measure of errors between paired observations expressing the same phenomenon. Examples of MAE, or rather examples of Y versus X, include comparisons of predicted versus observed, like in this case, subsequent time versus initial time, etc. So MAE is calculated as the sum of absolute errors divided by the sample size. So moving on to it, from sklearn, import metrics, print mean absolute error, mean, metrics dot mean underscore absolute underscore error, in bracket y underscore test, y underscore prediction. And it gave us this result of mean absolute error equals to 4.183859 and the rest of the figures. So let us check the accuracy of our prediction using a graph. And after plotting the graph, we can see number of hours studied. We can clearly see that the difference between the predicted values, the line for the predicted values, and the line for the actual scores isn't so different. So we can conclude from our graph above that the error isn't much. So thank you so much for listening, everyone, and please comment, like, and most especially evaluate my task. I wish every other person attempting this task a good success. Thank you so much.